We have seen before that when f in n plus 1 variables is a homogeneous polynomial of degree 1, so a linear function, then its vanishing locus is a linear hypersurface, also called a hyperplane. And then one can check, and we're going to do this in the end of the video, that there exists an isomorphism of Pn to Pn, which sends this linear hypersurface to our favorite hyperplane, namely the hyperplane at infinity, cut out by the equation x0 equals 0. And then with this observation, we can see that the complement of this hyperplane gets sent by this isomorphism to the complement of the hyperplane at infinity, and we know what that is. That is just affine space An. And so what this shows is that if from Pn we remove a hypersurface of degree 1, then we get an affine variety. And this statement holds more generally for hypersurfaces of arbitrary degree. And this is what we're going to show. And the tool that we're going to use is the so-called Veronese embedding. And this is the following. So we fix n and d, positive integers, and then we let f0 to fn be the set of degree d monomials. So this big N is then exactly this n plus d choose n minus 1, because we start with f0. This is the number of such degree d monomials. So for example, for n equals 3, d equals 2, we have the following. We have x0 squared, x0, x1, x0, x2, and so on until f5 is equal to x2 squared. So we just enumerate them a priori in any order that we like. It's not so important. And then we can consider the map f from Pn small n to P big N, which takes x and just sends it to this vector, where we just evaluate all of these degree d monomials on x. And the first note here is that we claim that this morphism is actually defined everywhere. And for this, we need to check that this vector here isn't 0, but well, the vanishing locus of all of these degree d monomials in particular, you have to have that all the dth powers of variables vanish. And then this vanishing locus here, this would force x0 up to xn to all be 0, but we know this is not allowed in Pn. So in fact, this vanishing locus is empty. So basically the radical of this ideal would be this irrelevant ideal that we have seen before. And so all of these components of this map big F don't vanish simultaneously. And then we had a lemma which says that for such a map given by homogeneous polynomials of the same degree, this is defined exactly where this doesn't vanish simultaneously. So in other words, this gives a morphism defined on all of P small n. And we can observe now, using the theory of complete varieties that we have seen before, that the domain of this morphism is a complete variety, and the target, well, it's also complete variety. In particular, it's a variety. And then we know if you go from something complete to a variety, then its image, which we call x, is a projective variety. So whatever this map does, at least the image is closed inside the P big N. And then the big claim, and the reason why this thing is called the Veronese embedding here, is that this is an isomorphism. In other words, F is a closed embedding. So somehow this map to its image is an isomorphism. And to prove this, I mean, certainly it's surjective, and what we can do is we can write down an inverse morphism on some open cover of this X. And we choose our favorite open cover, so we can in particular look at here at this locus of points where xi is not equal to 0. And then under F, this maps somewhere, and in particular, of course, if xi is not 0, then also xi to the d is not 0. But xi to the d, this is one of the components of this morphism. Let's say we order them so that it's actually the ith component. Then we can see that the ui maps exactly to the locus of points in X where this ith component is non-zero. And clearly this is an open subset. And in fact, as we have seen before, these open subsets, so if you were in the complement of all of these vi, then all of the xi to the d would have to vanish, and this gives you exactly the empty set. So in fact, these vi cover the target. And so we can hope that we can define the inverse of the morphism on that cover. And then just to see how do we get back. So we started with the vector x, and then we have extracted these all of these monomials in x. We want to get back to the vector x. How do we do this? Well, first of all, we see this ui here is just isomorphic to an. This is one of the standard patches of Pn. And the coordinates there are just x0 up to xi minus 1, and then we skip the xi because we set it to 1, and then we have xi plus 1 up to xn. So we have to extract these coordinates here from the image of f, but then you just see you can get back xj by taking this monomial here of degree d and dividing it by this monomial of degree d. And you see this is a regular function on this vi, because vi is just the locus where xi to the d is non-zero. So we're allowed to divide by this. And you see both of these are just given by coordinate functions on the vi, because they're both degree d monomials. And so we can see that we can write down the f inverse from vi to ui. It's given by these regular functions, so it gives us a map to an. And so this shows that f is injective and the inverse is a morphism. As I said, this can be checked on this cover here. Okay, and then some remarks about this Veronese embedding. So first of all, we see it realizes this projective space as a closed subvariety of some bigger projective space. And you could ask, I mean, what does this help? We were already a projective space. Why do we have to go to a bigger one? The advantage here is that f can relate degree d polynomials in the coordinates xi on Pn to linear polynomials in the coordinates yi or yj on the P big N. And these things are then called the Veronese coordinates. We're going to see some examples, but essentially, I mean, if you have some linear combination of degree d polynomials, then just take the same coefficients, but replace the monomials by the corresponding linear coordinates on Pn, and then you get a linear function here, whose pre-image is a degree d function here. And one more thing, of course, we can't just do this for Pn. But if you have y inside Pn projective, then if you restrict the Veronese embedding to y, then of course this also embeds this y in this bigger projective space. Let's see some baby examples here. So the most trivial ones are, first of all, if you set d equals 1, then you just have degree 1 monomials. These are just the coordinates x0 up to xn. And so in fact, this Veronese embedding in this case is just the identity map from Pn to Pn. A bit more interesting, if you set n equals to 1, so the domain is P1, but the degree can be arbitrary, then you get exactly this map sending P1 to PD, and this thing here to all the monomials of degree d. You can order them in this way. And this map or its image is then often called the rational normal curve of degree d inside PD. Okay. And a fun exercise here is the first part is that you try to find explicit equations describing this image of the Veronese embedding inside here. And the hint is you can actually find a system of quadratic equations cutting this out. And if you find the system of quadratic equations, then in the second part, you can show that any projective variety x is isomorphic to the zero locus of some quadratic polynomials inside some big projective space. So somehow we know by definition the projective variety is isomorphic to the zero locus of some homogeneous polynomials of some degree in some projective space. But in fact, using this Veronese embedding, you can show that you can always restrict to quadratic polynomials. Note, however, very important. This is not saying that if x is inside some Pn, that you can describe this x inside that Pn as the zero locus of quadratic polynomials. This wouldn't work. But it says that possibly you need to embed x into some bigger projective space. And if you're willing to go to this bigger space, then on there, you can cut it out by quadratic equations. Okay. And then the corollary that we started with, the kind of motivation here, if you recall, we started with the motivation that if you have Pn, you remove a linear hyperplane, then you get something affine. And now we're going to the more general setting and saying that if x is a projective variety and you have a homogeneous polynomial, which is non-constant, so of positive degree, then x minus the vanishing locus of this polynomial is an affine variety. So once you remove any one of these hypersurfaces of positive degree, then you are an affine variety. And the proof proceeds by going first from special cases to the general case. And the first one is that what we already know, that if f is the polynomial x0 and x is all of the projective space Pn, then if we remove this hyperplane at infinity, you get an, which is an affine variety. So that's done. And then the second one is this check that we promised that if f is any linear polynomial on Pn, so for example, something like this here, then we want to prove the statement, and for this we choose a matrix. We choose a matrix A. The first row is this just this set of coefficients of f. We know this first row is non-zero because we want to have that f is a non-zero, non-constant polynomial. So we have one row which is non-zero, and then we just extend this somehow to a basis of k to the n plus 1. So we fill in some entries here so that we get an invertible matrix. And then the claim is, well, this invertible matrix then defines an isomorphism from Pn to Pn. We have seen these things. These are these kind of projective automorphisms of projective space. And then you check that if you start with a vector where f of x is non-zero, it exactly maps this to a vector where y0 is non-zero. This is why we chose this to be the first row. And so we see that under this isomorphism, x minus v of f gets sent to, well, this locus here, which is just an. And so this shows that this is still affine. So if we remove any linear hyperplane, then we're still in affine space. And now we go to the higher degree case and we use the Veronese embedding for this. So if f is any homogeneous polynomial of degree d and x is projective variety, then we do this trick of saying, take the coefficients of f and then put them in a linear polynomial g in these Veronese coordinates, y0 up to yn, which corresponds to, so g is the linear polynomial corresponding to this degree d polynomial. And then just basically by this definition, the corresponding Veronese embedding sends this vanishing locus of f to the vanishing locus of g. So in particular, kind of the, yeah, exactly. So somehow the preimage of the vanishing locus of g is the vanishing locus of f. And then we just see, I mean, somehow this y, which is the image, which is annotation for the image of the Veronese embedding. This sits inside this big projective space, P big N. And so once you remove v of f, you sit inside y minus v of g, which sits inside Pn minus this vanishing locus of g. And then we have this lower row. So somehow then we see this is what we're interested in, x minus the vanishing locus of f. This sits as a closed subset because x is closed in Pn inside here. This is isomorphic to y minus the vanishing locus of g, and y was sitting closed inside Pn. So this is closed inside here. So all of this composition here is a closed subset. And then we know that Pn minus the vanishing locus of this linear polynomial G is an affine variety by the proof above. And then this sits inside here as a closed subset of an affine variety. Somehow this here is affine. And then if you're closed inside an affine variety, then you're also affine. And this finishes the proof. So somehow this shows that also X minus this hypersurface is affine. And so this here was maybe a bit abstract, so I want to finish with one concrete example. Of course, it's a small example so that we can see what goes on, but let's say you wanted to show that P1 minus the vanishing locus of this polynomial here is 0. So this vanishes exactly basically in affine coordinates as 0 and 1. And then what you do to show this is you embed this via so this is degree 2 polynomial, so you embed it via degree 2 Veronese embedding, like this. This exactly gives you can check, this gives you this vanishing locus of this kind of standard parabola. And you see the Veronese coordinates y0, y1, y2 correspond to these monomials here. And then this f, so this x1 squared minus x1, x2, corresponds to the monomial here y2 minus y1. So this is G under this translation. And then you see this is the vanishing locus of G, and it intersects exactly in these 2 points corresponding to the image points of these 2 points here in P1. And then because P2 minus the vanishing locus of G minus this line is affine, the blue part is then closed subset of this affine space. And so this shows that this blue part here is affine. So this was the proof of the statement and the discussion of the Veronese embedding, and that's also the last part of this chapter.